Video number 123, calculating eccentricity for ellipses and hyperbolas. The eccentricity, this is a definition, a new word for us here in pre-calculus. The eccentricity, by all rights, is basically an attempt to quantify the roundness and or flatness of a conic section. The two eccentricity values we're going to discuss in this video, and the ones you'll primarily see discussed, will be only for ellipses and hyperbolas. However, there probably is a way to calculate the eccentricity value for a parabola as well. Alright, let's go ahead and get the job done here. The eccentricity for an ellipse, hope you don't mind my notation here, E sub ellipse, is equal to C divided by the bigger value between A and B. That's simple. For a hyperbola, it's going to be C divided by the first value that you see, A or B. Okay, and we'll definitely see a couple examples here of each. Here's the first one. We've got, find the eccentricity value for the following equations. There you go. All right, I should have just said equation, but that's fine, yeah. X squared over 16 plus y squared over 25 is 1. The eccentricity of the ellipse is equal to C divided by the bigger value. Well, what's bigger? A or B? Definitely B. B is 5. Right? C value is going to be 3 because when it's a plus, you do subtract. So we do 25. We know that C squared equals 25 minus 16. Therefore, C is 3 because you do the square root of 9. Alright? 3 over 5, 0.6. Now, it also helps for us to understand what it is we're actually calculating. Let's go back to this first page here. And I want to go through here because it does us no good to know that it's 0.6 and not understand what it means. Here's what it means. Alright? Let's just take an ellipse. Alright? If we took a look at a circle, an ellipse, a flatter ellipse, a real flat ellipse, okay? What we could say is now a circle has a center. This ellipse has two foci that are close together. This ellipse has two foci that are further apart. And as the flatness is increased for each elliptical shape, the C value gets larger. Here, C is 0. Here, C is small. Okay, C is small. Here, C is large. In other words, C is definitely less than A, right? Because here's A, right? But C is, it's always going to be less than A, but in this case, wouldn't you say, for this last one, as the ellipses get flatter, we would say that C is almost A, and it never will be. However, the flatter the shape, the closer that C gets to A, so C gets real close to 1 as the shape gets flatter. Okay? And some students have had, say if it's a line, it's 1. Well, a line's not an ellipse. So what we could say for an ellipse is that the maximum height is 1. Why is it the maximum? Because C is small here, A is definitely large. So wouldn't you say that C over A is definitely closer to 0 than it is to 1? Okay? Here, C is definitely 0 for a circle because what is C? It's a distance from the center to the foci. Okay, here there is no distance, so therefore we would say that 0 to 1. What could we say? 0 would be the roundest. So the smaller the eccentricity, the more rounder it is, and then the larger, or in other words closer to 1, the flatter, the more flat the ellipse is. So we basically have a range, so we almost have a percentage of flatness really. So you have a this would be like, you know, a 95% flatness. This would be like a 50% flatness. This would be a 0% flatness, right? So basically closer to 0, more round, closer to 1, flat. Alright, so they tried to scale it off being a percentage. It's pretty neat. Anyway, let's get back to the show of calculating. If we were to find the eccentricity here, this is definitely an ellipse, so our formula would be to do c divided by the bigger value. What's bigger, 10 or 3? 10. Square root 91 over 10, 0.95. So this would definitely be a very flat ellipse, and you can tell because look at this. 10, you'd go 10 units east and west, and you go 3 units north and south. That's a flat ellipse. Here the numbers are relatively close together, so you get 0.6. It's kind of a medium flatness there, as you can see. Here's the eccentricity for a hyperbola now. Now hyperbola things are going to be a little bit different. You're going to do c divided by not the bigger, but by the first amount between a and b. Not the bigger amount, but the first amount, which is why we use a 4. 16 shows up before 25. So we use the 4. Alright? So it's square root 41 over 4, which is actually 1.6, which is greater than 1. So this little strategy we discussed over here, the roundness and flatness, this is only true for ellipses. For hyperbolas, it's a little bit different, and the reason is because, the reason is this, your hyperbola can be as flat as possible. I mean, so this foci would be way out here. You know, the C value is way out there. Okay. You know, if you have these two, this hyperbola, which we haven't really discussed hyperbolas yet in this vlog, but we will be very soon, so you'll want to obviously come back to this perhaps later. But this would, you know, this where your foci are going to be over here. So the foci could be way out there. So there's no limit, I guess, for hyperbolas. I believe it's actually the smallest, I think, is 1. And it goes to infinity. I think 1 to infinity ends up being what you're going to use. And the reason it's 1 is because how are you getting c, right? For ellipses, what are you doing? You're adding 16 and 25 together. That's how you're getting square root 41. So then, of course, this number is always going to be what? Smaller. So the smallest it would be is 1 to infinity. Alright, then the last one here again, you just take c divided by the first amount. I don't know why I did that here, but anyway, opportunity for you to learn. Yeah. Opportunity for me to learn and you to learn, yeah. So square root 109 over 10, 104, 1.04. See that? 1.04. As you can see here, this would be, this would be a very, well, let's take a look at it. Let's take a look at it. Let's just summarize this now. Negative 7 comma 0. That's the center. And then the way we do this, you're going to go to the east and west 10, so that's going to be a negative 17, that's going to be a 3. You're going to go up 3, down 3, so it's going to be a very skinny asymptote. This way, which way are we going? Oh, it's very skinny, yeah. So actually, the closer to 1, the skinnier, so we were right. The closer to 1, the skinnier the hyperbola is. Alright? So good times, guys. And I would imagine this is probably the same thing if they were to ask you to do eccentricity for a parabola, but they don't have us do that. So for this video, just eccentricity for ellipse and hyperbola. Good times, good luck.